Okay, this is what questions will look like in the exam. Okay, so it describes a situation. It doesn't tell us what kind of distribution to use. It does say use a distributional approximation. So we know that we're going to use one of our bank of distributional approximations. Now at this point, we've only done one, and it also tells us what to do in brackets in the question. But in an exam, you wouldn't have those hints. So what you have to do is look at the situation. We've got glass jars, and each glass jar has got a 0.02 chance of having a flaw. And then we've got 180 jars, and we're interested in how many flaws there are altogether in those 180 jars. So I'm counting the number of flawed jars out of 180. So we recognize that as being counting successes, doesn't have to be the conventional view of success, out of a fixed number of trials. And we're going to assume these trials are independent, and we're told the probability is 0.02, so that's fixed. So therefore, if we're counting successes in a fixed number of independent trials, then this is going to be binomial. So x, the number of flaws, is going to be binomial. Okay, and I need an n and I need a p. Okay, n is the number of trials. How many trials are there? There are 180 jars, so it's a binomial with n is 180. Okay, and what's my probability of success? Well, success is having a flawed jar. So that's a 0.02 chance of what we're calling success. So I've got a binomial distribution. Now, n is 180. Now that is large. Okay, why do I need to care? Because remember, I'm using a distributional approximation, and I need to check the conditions apply. So p is 0.02, which is small, and n is large and p is small, means that I can use a Poisson approximation. So this is the exact distribution that I've set up, but we now need to set up an approximate distribution. So my approximate distribution is going to be x is a Poisson. Okay, all right, but I can't write down the Poisson yet because I don't know the parameter. I need a value of lambda. So my parameter that I need is, my parameter is lambda, which is the mean. So I need the mean of the binomial. So here was the binomial. How do I work out mean of a binomial? Well, remember, all of these formulas are there in your blue formula book. Here they are. Okay. So it tells me, for a binomial, forget this column, but mean of a binomial is this, variance is this, mean of a Poisson is the same as its variance, which is lambda. So don't forget you've got this. This is page 11 of your formula book. So mean of a binomial. So I've got a binomial. I want its mean. So that's NP, which is 180 times 0.02. Okay, which is 3.6. So therefore, that's my value for lambda. So I need a Poisson with a lambda of 3.6. And now all I've got to do is find the probability that x is, well, what do I want? I want there to be more than 3 flaws in those 180 jars. I've used the 180 jars, more than 3 flaws. X is greater than 3. How do I do this? Well, I must do the diagram of outcomes. Really get into this habit. So, all the values, 0 is the lowest value. I'm interested in values near 3, so let's do 2, 3, 4, ... Okay, there is no highest outcome for a Poisson, though there would be for this binomial, but never mind. This is all you need to draw for your diagram. So ticks and crosses. I want to be greater than 3, so 0 doesn't work, 2 doesn't work. I need to be actually greater than 3, so 3 doesn't work, 4 does work, everything after 4 works. I need a box that captures all the ticks. So my big box is going to have to capture everything. Okay, and now I need to get rid of the crosses. So I need a box that gets rid of all the crosses. So big box minus little box. Big box catches everything, just means I'm doing 1 minus. Okay, so the other box I am going to have to use my calculator for. The crosses I've got to get rid of is the probability that x is less than or equal to 3. So now I've got a probability that I can get from my calculator. So second screen under menu 7, Poisson CD. Remember, we're never going to use PD. So I want a variable to, and my x value, I want less than or equal to 3. That's this one here. Okay, and I want a lambda of 3.6, and the calculator tells me that that probability is that. So I need to do 1 minus 0.51522, and that gives me the answer, which is 0.48478. And that is my answer to 5 significant figures, which is fine. Good. All right, so the second one here, all right, is another situation. All right, once again, we've got something with a 2% chance of happening. Now, 2% is a probability. It's the chance that the bulb will break during shipping, and that is a value of 0.02, so I've got the same probability as before. Now I've got sets of 60, and I'm counting the number of bulbs from a box of 60 that will break. Okay, and I want that number to be more than 2. So this is a very similar example. Okay, I've got 60 trials, 60 boxes, in each, 60 light bulbs in a box. Each light bulb has got a fixed chance of breaking, and I'm counting the number that break. So I am counting the number of successes, breakages, in 60 independent trials. So for this one, for part B, X has a binomial. How many light bulbs in a box? 60. So there are 60 trials, so my N is 60. And my P, what's the chance that a light bulb breaks? It's this 2%, which is 0.02. So I've got a P of 0.02. Okay, what comments can I make? Well, N, which is 60 is large. Anything above 50 is large. Okay, and P equals 0.02. Anything below 0.1 is small. So I've got a large N and a small p, so I can therefore use Poisson. It's fine. Once again, why am I doing an approximation? You wouldn't do this unless you were told to, but it says use a distributional approximation. Okay, so the appropriate one, when n is large and p is small, is a Poisson approximation. It's the only one you know at the moment. So, what do I need for Poisson? I need my parameter. What parameter do I need for a Poisson? I need lambda. Lambda is the mean. How do I work out the mean? As before. The mean comes from the mean of this binomial, and the mean of a binomial, from page 11 of the formula book, is NP. Okay, so my NP is 60 times 0.02, okay, which in this particular case is going to give me 60 times 0.02, it's going to give me 1.2. So I need to say that approximately, so my approximate distribution, this was the exact distribution, the approximate distribution is X, is a Poisson with parameter 1.2. How do I get a probability from that? Well, I need to set it up. I need to get back to the question, don't I? What probability do I want? I want the probability that it's more than 2 bulbs breaking. Okay, so I want the probability that X is greater than 2. So, diagram of outcomes. I need 0, I need 2 and values nearby 2, which is 1 and 3, ... There is no highest value for a Poisson. Do I want 0? No, I want to be greater than 2, so I don't want this one, I don't want this one. I can't equal 2 because I've got to be greater than 2, but I can have 3, and I have all of these. I need a big box that captures all the ticks, so that's got to include everything, all of these ones, so it's going to be a 1 minus. The big box is all the outcomes, and then I need a small box that gets rid of the crosses I don't want, which is the probability that my X is less than or equal to 2. All right, so you can see it. So big box is 1 minus the crosses that I don't want, X less than or equal to 2. Okay, the 2-box diagram is your friend. Okay, probability of X being less than or equal to 2, well, I can just change what I did before. It's a Poisson again. This time I want to be less than or equal to 2, and my lambda is now 1.2. So that probability is that thing there. So I need to do 1 minus that probability, 8, 7, 9, 4, 9. So I'm going to get 0.12051, which is my correct probability to 5 significant figures. So that's a fairly straightforward process.